Is my screen visible for you, my dear?
Yes, sir.
Okay. So
Yes.
this is the last question. So this is one of the important question also. So read the question very carefully. What is given in the question? Read the question very carefully. The electric field in a certain region of Earth atmosphere is vertically downwards. That means you have the Earth and your electrical fields towards the Earth is vertically downward direction. At an altitude of 300 meters, the field has magnitude 75 Newton per Coulomb. At a height of altitude 200 meter, the magnitude is 210 Newton per Coulomb. Find the net amount of the charge contained in a cube 100 meter on edge with the horizontal faces of altitude 200 and 300. So what is given in the question? First of all, I will draw the picture and then I will explain. You have the earth surface. Okay, my dear, listen carefully. So you have the earth surface. So this is earth. You consider this is our earth. And above the earth, you have the structure of cube. So what is the shape of the cube? All sides are equal. Am I right? Am I right or not?
Yes, you are.
So I'm just drawing the cube. I will tell you why I just draw the cube, because in the question they clearly mention. So I just draw the cube, and the cube has all sides are equal. So what is happening here? You have the earth, and then the vertical lines are vertically downward. That means electrical fields are vertically downwards. You can read the question first line. The electrical field in certain regions of the earth atmosphere. So surrounding the earth is a earth atmosphere. Am I right? So top of the earth, you have the cube-like structure. So your electrical field lines are vertically downward direction. So I can change the color. By that you will get an idea. So you have electrical field lines downward direction. Clear, my dear? So you have the electrical field lines. So all these red color are electrical field lines. And now you can see top of the earth, you have the cube-like structure, and the cube top side, that means the upper side of the cube, this is the upper layer, this is the lower layer. Clear? Understand?
Yes.
Okay. What is the height of the upper layer? The height of the upper layer is, what is the height of the upper layer? It's 300 meter. What is the height of the lower layer? What is the height of the lower layer? 200 meter.
200.
You get my point, my dear? Understand? And this is earth. So we have the earth, and surrounding the earth is the earth atmosphere, and the red color electrical field lines are vertically downward direction, and above the earth you have the cube having both upper layer and the lower layer, and the upper layer height from the earth surface is 300 meter, and from the earth to the lower surface of the cube has 200 meter. And then to the upper layer, what is the electrical field? What is the electrical field strength? What is the electrical field strength at the upper layer, my dear? Just
75.
75 Newton per Coulomb. And what is the electrical field at the lower?
210.
210. Why it is 210? Why it is 75? Because whenever the closer to the earth, because the charge particles are here, so wherever it is close to the earth, the electrical field strength will be greater. Whenever you are moving with certain height, the electrical field strength can be weaker. So according to this picture, my electrical field strength at the top layer is lower value when you compare with the lower value. Am I right or not? So the upper value of the electrical field is lower. The downward layer of the cube has the higher electrical field. Understand, my dear? So this is the picture which explains the clear information about the question. Is there any doubt from this picture? Is there any doubt?
Clear, doctor.
Okay, now what we are going to do? We are going to find the net amount of the charges. So inside this cube, you have some charges. So we have to find the value of charge. So this is our ultimate aim. What we are going to find? We are going to find the value of the charge. So before that, we have to know the clear information. So all the electrical field lines are passing through the upper layer and it is coming out of the lower layer. Am I right or not? Am I right or not? Because you can see from the upper layer, the field lines are entering, and from the lower layer, the field lines are coming outside. Am I right? Am I right or not?
Yes.
So when the field lines are entering the layer, is it positive or negative?
Positive.
I explain. What is your flux? When the field lines are entering the area, your flux lines will be negative. And when the field lines are coming out of the area, it has the positive. So the flux in the upper layer has the negative value and the flux in the lower layer is positive. Am I right? Am I right or not?
Yes, you are.
Okay, so we have to find the resultant flux. What is the resultant flux? Greater value minus smaller value. So here our greater value is the lower layer. So what I am going to do, flux in the lower layer minus flux in the upper layer. Clear? Clear?
Yes, doctor.
What is the formula for the flux? The formula for the flux is nothing but electrical field multiplied by area. This is the rule we already studied. So I am going to use this formula here. So what you will get? Area multiplied by electrical field at the lower minus area multiplied by electrical field in the upper. Am I right?
Yes.
Am I right? So I am going to take the area as the common term. So I take the area outside. So what is inside? Electrical field in the lower layer minus electrical field in the upper layer. Now you can see we have the electrical field of the upper layer and we have the electrical field of the lower layer and we have the value of area. Now what I am going to do, I am going to substitute the value. My dear, you have two areas with a 100-meter length. So this is our first area, this is our second area. So I have 100 square. Am I right? Am I right or not?
Doctor, where mention the area?
You can see they said the edge length has the value of 100 meter. So this is your 100 value. This another one is here because you have to consider only the flux line entering the area. So this edge length is 100. Am I right? Am I right or not? Do you get my point?
Yes, you are right.
So you have two area with the edge length, which is one is 100 here, another one is 100. So I have to write 100 square multiplied by my lower electrical field. What is our lower electrical field, my dear? Our lower electrical field is 210 minus our
Minus
upper electrical
75.
field is 75. So when you substitute, you will get the flux. Am I right? Am I right or not?
Yes, you are.
Now I am going to use the another formula for the flux because we have two formula for the flux. The first formula is this. What is the another formula for the flux? The another formula for the flux is Q enclosed divided by epsilon naught. Am I right? We already studied this rule. So for finding the charge, I am going to use the second formula. So flux phi, which is equal to Q over epsilon naught. Therefore, Q, which is equal to flux multiplied by epsilon naught, and epsilon naught is the constant. So in the first part you got this answer. Take this answer, substitute here, multiply by 8.85 multiply by 10 to the power of minus 12, you will get the net charge. Understand? Clear?
Doctor,
Yes.
there is a unit for flux.
Of course, there is a unit for the flux. What is the unit for the flux? You can see here. Flux formula is electrical field multiplied by area. So what is the unit? What is the unit for electrical flux? The electrical flux unit is Newton per Coulomb. Am I right?
Yes.
And what is the unit for the area?
Yes, doctor.
Clear. So electrical flux has the unit. But what is the charge? What is the unit for the charge? The unit for the charge is Coulomb. That's it. Clear.
Clear, doctor.
Clear, my dear.
Doctor, again, please. Why did you take the lower limit subtract by the upper limit?
Because your lower electrical field is greater. Because your lower field, because you can see the red line, The red line is entering the upper layer. Whenever the field line is entering the layer, it has negative value. Whenever the field lines is leaving the area, it has positive. So positive is the greater value. Am I right?
So according to the science, yeah, I get it. Thank you.
According to the sign, because we have to decide the sign based on the field lines entering the area. If the field lines entering the area, it has negative. When the field lines coming out of the area, it is positive. Clear?
Okay. Yes, clear. Thank you.
Okay, that's it. My dear, chapter 23 is over. Now I am going to start chapter 24, and inshallah for our midterm portion, so not midterm portion, our quiz 2 portion, 3 chapters. What are the 3 chapters? Chapter number 22, chapter number 23, and chapter number 24. Inshallah, you are going to write your quiz 2 in week number 11. Clear? Understand? Understand?
Okay, doctor.
Clear.
Okay, good. Now I'm going to start chapter number 24. What is this?
Doctor,
Yes,
we are in week
9.
9.
Yes.
2 weeks.
So next week is week number 10, and after the week you are going to write your quiz too. Clear?
Clear.
Okay. My dear, this chapter is very easier one, and you are going to study only 3 formulas. How many formulas you are going to study? Only 3 formula. And my dear, from chapter number 21 to 24, you will get the formula. Some of the formulas are exactly similar to each other. So I will tell you the clear picture. Could you please tell me what is Coulomb's law? Could you please tell me what is Coulomb's law?
F equal K Q1.
F which is equal to K Q1 Q2 over R square. Am I right?
Yes.
What is the formula for the electrical field? E which is equal to K Q over R square. Am I right? Am I right?
Yes.
And today you are going to study 2 formula. The first one is U, that is electric potential energy, which has the formula K Q1 Q2 over R, and another one electric potential K Q over R. You can see the 4 formulas. These 4 formulas are exactly similar to each other. Am I right? Am I right or not?
Yeah, doctor.
Yes, doctor.
Yes.
So please, whenever you are answering the question, especially from chapter number 21 to 24, read the question very carefully. What type of information is given here and what we need. All the informations will be given clearly in the question. So if the question is related with the potential, then you have to use this one. If the question is related with the electrostatic force, then you have to use this one. If the question is related with the electric potential energy, you have to use this one. If the question is related with the electrical field, you have to use this. So in this chapter, you are going to study these 2 important formula about electric potential energy and electric potential. So what are the topics today we are going to discuss? We are going to discuss 4 important topics. First one is electric potential energy, because you will get some formula. Just before I told you, electrical potential energy is indicated with the letter U, which is equal to K Q1 Q2 over R. This is our rule, whether capital or small r, no issue. And here electric potential V, we are going to find V which is equal to K Q over R. And the equipotential surface, some theoretical question will be coming from this topic. And here you will study one formula, work done, which is nothing but amount of the charge multiplied by the change in potential. And finally, the 4th formula, we are going to find the relations connecting electrical field as well as the potential. What is the relation connecting electrical field and electric potential, which is nothing but negative of gradient of V. And I will tell you what is this later. Okay, so these are all the 4 formulas today we are going to study from this chapter. So please, my dear, listen carefully. And this slide represented the definition for the electric potential energy. Definition. What is the definition? The definition is given in these 3 lines. Suppose if you ask the question, define electric potential energy. So what you have to write? You have to write the amount of work done by bringing the charge Q2 from infinity to point P. So initially you have charge Q2 at infinity position. That means very far away from charge Q1. So what you are going to do, you are going to bring the charge and you are going to place the charge Q2 at point P. So if you want to move the charge Q2 from infinity to this point P, what you have to do? You have to do some work. Am I right or not? Because both are positive charge. So here, when you place two charges, two positive charges, what will happen? The force of repulsion will be more. Am I right? Am I right or not? Whenever you bring Q2 positive charge from infinity to this point, what will happen? My Q1 is positive, my Q2 is positive. What will happen? It will repel. So if it is repel, then you have to do some work to bring the charge and put the charge Q2 in the location of P. So you have to do some work. So the explanations are clearly given in the next slide. My dear, listen carefully. I explain everything in the easiest way. So please listen carefully. See the picture first. So initially, I have only one charge Q1. And now I have another charge Q2. Both are positive. I am going to bring this Q2 from infinity to a point P. So what will happen? This Q1 and Q2 are both positive. So electrostatic force of repulsion will be there. But what is our ultimate aim? We have to take this charge and we have to put the charge in this point P. So what is the distance between Q1 and P? Capital R. So what I have to do? I have to do some work. So in physics 1, we already studied the formula. What is the formula for work done? F dot D. Am I right? Did you know this formula, my dear?
Yes.
So we are going to use this. So what I am going to do, my dear, see the relation. I put a two relation. That means this is the work done by myself. This M stands for myself. Or you can say your name. So here M stands for Mustafa. You can just take like that. So I have to do some work. That means I have to take the charge from infinity to the point. So I have to use some work for my own work. That means I have to do the positive work from this point to P. So at the same time, what will happen? My dear, listen carefully. I am bringing the charge from infinity to point R. But what will happen based on this charge Q1? Q1 is positive, so it will repel. So what this Q1 do? It will do the charge Q2 to move away from Q2 from R to infinity. Am I right or not? You are moving from infinity to R, but the charge Q1 is moving R to infinity. That's what I'm just using the relation alpha. That means infinity to R is my limit, but the charge Q1 has the limit of R to infinity. Understand? So the concept based on the repulsion. So one force, you are going to pull the Q2 from the right hand side to the left hand side, but the charge Q1 moving charge Q2 from left hand side to right hand side. Am I right? That's what I put two arrows. So this is the force by myself, and this is the electrostatic force based on the charge Q1 and Q2. Clear? Understand? Clear, my dear?
Okay, clear, doctor.
Now listen carefully. We don't have any formula for myself because I have some force. I don't have any formula for myself, but this force, this arrow is exactly equal to this arrow. I don't have any formula for my force, but I have the specified formula for the electrostatic force because we know the Coulomb's law. What is Coulomb's law, my dear? Just before we write the Coulomb's law, what is Coulomb's law? K Q1 Q2 over R square. Am I right? So now you can see I can use this. Once I just use the Coulomb's law for this part, this answer must be equal to this answer. Am I right? Am I right or not?
Yes,
Am I
doctor.
right or not?
Yes.
So in this place, I'm going to take this value. I'm going to substitute here. If you substitute, what you will get? Q1, Q2, 4 pi. Brother, here I expanded this K. What is K? 1 over 4 pi epsilon naught. Am I right? So I expanded the value of K. That's what I write. Q1, Q2 over 4 pi epsilon naught multiplied by R square multiplied by dr. So now my limit exactly from R to infinity, because the force by myself is infinity to R, but the force of the electrostatic force from R to infinity. Now I'm going to take all the constant term outside. So these are all the constant term. I take it outside the integration because you already studied in calculus 2. Whatever the constant you have to take, you can take it out of the integral. Am I right? So the integrating component is R square. So 1 over R square. If you integrate 1 over R square, what you will get, my dear? It is nothing but minus of 1 over R. You already studied in calculus 2. If you integrate 1 over R square multiplied by dr, you will get minus of 1 over R. Now I am going to apply my upper limit. When you apply the upper limit, what will happen, my dear? 1 over infinity is 0. Am I right? And when you apply the lower limit, this small r is converted to capital R, because our ultimate aim, this is the distance from Q2 to the point P. So what is my R? So when you substitute the lower limit, this small r is converted to capital R, and finally minus into minus become plus. I will get this equation. Actually, this is my work done, and this exactly says about your energy. Because what is the definition for work? The work is the amount of energy to do. Am I right or not? We already studied in physics 1. Whatever the energy you have, that is nothing but your work. Based on the energy, you have to do some work. Am I right? So my work done is nothing but the energy. So I can replace this W in terms of U. And finally, I got this equation that is nothing but U, which is equal to 1 over 4 pi epsilon naught. I can write as K and then charge Q1, Q2 over capital R. Clear? Clear, my dear? Clear?
Yes.
Yes.
This is the
Okay.
electric potential energy.
This is electrical potential energy. So this is the theoretical background about this formula. How we got this formula? We have to use this type of concept. The most important thing, the electrostatic force of repulsion. So you have to take the like charges here. If you take unlike charges, it will be immediately attract. Am I right or not? It is meaningless. Am I right or not?
Yes,
Right or
you
not?
are.
Yes.
That's what I'm using. If you take both positive charge or both negative charge, the concept remains the same. Clear? Clear, my dear?
Clear,
Yes,
doctor.
Yes.
Okay. Now it's exactly, when you just see this, no need to worry about this slide. This is just a comparison of electrical potential energy and the gravitational potential energy, because we already know the gravitational potential energy is mgh. We already studied this formula. Work done, which is nothing but force multiplied by distance, height. You can see the picture. If you want to raise any object from certain height, this is my distance. So F dot D, here F dot H. F dot H is nothing but force is nothing but mg, so H is there, so mgh. Likewise, if you just see the concept of electrical potential, so actually this is the explanation for electrical potential energy, this is the explanation for gravitational potential energy. Clear? So both will be exactly similar to each other. This is just an explanation. The most important thing, the distance matter. Based on the distance only we got this. Clear, my dear? This is just the comparison. Let's come for the superposition principle. What we studied in superposition principle? Suppose if you have more than 2 charges, so we have here 3 charges. So Q1, Q2, what is the distance between Q and Q2? R12. And the distance between Q1 and Q3 is R13. And the distance between Q2 and Q3 is R23. We already know the formula. We already know the formula for electric potential energy. What is the formula? U, which is equal to, what is the formula, my dear? K Q1 Q2 over R square. This is the formula. Could you please apply the formula for these 2 charges? If you apply this formula for these 2 charges, you will get this. Am I right? Likewise, if you
Doctor,
apply the
R
same
square,
formula, what?
R square or only R?
Sorry. This is R. This is not R square. Sorry. This is only R. So if you apply this rule for these 2 charges, you will get, and if you apply the same rule for these 2 charges, you will get the second one. If you apply the same rule for the third charges, you will get this. So finally, what you have to do? You have to take the vector summation. So you have to add all these things. Finally, you will get only one potential energy. Clear? This is the concept of superposition principle, and the explanations are given clearly in this slide. So this is the explanation for this slide. Okay, my dear, don't get confused. Both formulas are exactly same. You can see here, I got this rule and the same rule is here. Clear? So the explanation part is here. So this is our explanation part. Understand? Clear?
Clear,
Yes,
doctor.
doctor. Clear.
Okay. Now we come for the second important formula of this chapter. What is that? Electric potential. So the general formula for the electrical potential is nothing but, it should be indicated with the letter capital V. And what is the general formula for this? Work done divided by unit test charge. So what is the formula? V, which is equal to W over Q naught. Now you have to compare this picture with the previous slide picture. My dear, in the previous slide, we take 2 point charges, Q1 and Q2. But in this slide, what I am going to do, I am going to take 1 point charge, 1 test charge. Clear? This is the difference. I have to take 1 point charge, 1 test charge. What is test charge? We already studied in chapter number 22. What is test charge?
Always
What is
positive.
the charge?
Always it has one value, unit. And it will be always smaller in size, and it is always positive in charge. Okay, so here I am going to take 1 point charge and I am going to take 1 test charge. So when you just use this concept, you will get this rule, and the explanation for this rule is given here. So my dear, listen carefully. Again, the same picture. The only small thing is nothing but this is a test charge. Again, I am going to bring the test charge from infinity. I'm going to bring this test charge from infinity. What is our ultimate aim? We have to bring this test charge to this point P. So what I am going to do, I cannot be able to bring immediately. Why? Because it's a very large distance. So I have to move the test charge small portion by portion. So what I'm going to do, I'm going to move small distance. That is nothing but the distance between 2 points. So here I just show 2 points, point A and point B. So I'm just moving. I'm going to take this test charge from infinity. Now it is on the way. Now this test charge is at point A. So I have to move the test charge from point A to point B. Now, my dear, listen carefully. When the test charge is exactly at point A, we already know the rule for the electrical field. What is the formula for the electrical field? We already studied. What is the formula? Q over R square. Am I right or not? This is the rule. But when you place this test charge at the point A, what is the distance from this to this? We have the distance is x. So what I am going to do? I'm going to directly substitute this rule here. You can see here, I'm directly in place of R, I'm going to substitute the value of x. So if you substitute the value of x, what you will get in this rule? This is become E, which is equal to K Q over x square. Am I right? That's what I written here. Electrical field at point A, based on this distance, we know this is our rule, where R is the distance from the point charge to this point A. So according to this concept, my distance between the point charge and the point A is exactly x. So I have to simply replace this R in terms of x. So that's what I just written the value here. Here 1 over 4 pi epsilon naught is our K value. Clear? Understand? Clear, my dear?
Yes, doctor. Clear.
My dear, if I ask the question, at least please give your response. Please give your response. Otherwise, we cannot be able to see each other. At least by your voice, I will recognize my line is okay. Clear?
Clear, doctor.
Clear, doctor.
Okay. Now, the second thing, when you just move the test charge from point A to B, you have to do some work. So we know the formula for the work done, which is nothing but F dot D. This is the rule for work done. Am I right? But the small work done, because you are going to move from small distance, dx, and finally you are going to take the charge and you are going to place at point P. But when you just move from small distance, I have to write the work done formula as F dot dx. Now, my dear, listen carefully. Your electrostatic force will be in this direction, but you are bringing the charge to the opposite direction of the electrical field. So what should be your angle? Your angle should be 180. You are moving to the left hand side, but the electrical field is moving the charge to the right hand side. So both are in opposite direction. So what is your angle? My angle is 180 degree. Cosine of 180 is minus F dot dx. Clear? Clear, my dear? So this is the amount of work done for bringing the charge from point A to B. Now, what I'm going to do, I'm going to completely work out with the integration formula from this point to this point. So what I'm going to do, if I integrate this dW, I will get the information about the work done. Am I right? You already studied in calculus. So if you just integrate the small portion, you will get the information about the big portion. Am I right? So that's what I'm going to integrate this dW. What is my limit? I am bringing the charge from infinity to point P, point R, small r. This is the distance R. Am I right? So I have to bring the charge from infinity to the point P. So my limit is infinity to point R. That's what I just write. My lower limit is infinity. My higher limit is R. Now, what is our dW? We already find the dW here. So I am going to take this. I am going to substitute here. If you substitute, you will get this relation. Am I right or not? Am I right or not?
Yes, doctor.
Yes, doctor.
Okay. Now, what is our force? We already studied in chapter number 22. What is the formula of force for media? Force, which is equal to electrical field multiplied by test charge. We studied this relation in chapter number 22. Am I right? So what I am going to do, I am going to take this formula. I am going to substitute here. If you substitute, what will happen? Your equation will be like this. Am I right? Am I right or not?
Yes.
Now, we already calculate the electrical field intensity. Now I am going to take this E, I am going to substitute here. If you substitute, your equation will be like this. Am I right? Am I right or not?
Yes.
So now
sir.
I'm going to take all the constant term outside. What are the constant terms you have? You have point charge Q, you have test charge Q naught, and 4 pi epsilon is the constant, and I will take the negative sign outside, but only inside the integral I have dx over x square. When you integrate this, you will get 1 over x, and when you apply the upper limit and the lower limit, you will get, when you apply the upper limit, it will be minus 1 over r. When you apply the lower limit, it will be 0. So 0, anything with 0 is just a value. Am I right? So here, when you apply the upper limit, I will get only negative of 1 over r. So minus into minus become plus, and finally I got the work done. Now after you got the work done, we have the general rule. What is our general rule, my dear, for finding the potential? Work done divided by Q naught. So I am going to write the same relation, my potential, which is equal to work done divided by Q naught. So I am going to take this, I'm going to substitute here. If you substitute here, what will happen? Your equation will be like this, and your test charge Q naught get cancelled, and finally you will get this relation, and here 1 over 4 pi epsilon naught is the K value. That's what we got the answer. Clear? Clear, my dear?
Clear, doctor.
So this is the rule, but in exam we are not going to write all the things. The only final relation is very, very important. This is the explanation for the previous slide. Clear, my dear? Understand?
Yes, doctor.
Okay. Now again the same concept, the superposition principle. Suppose if you have 3 charges, you are going to bring the 3 charges to a point P, and both Q1 and the point have some distance. So you know the rule. You know the rule between this Q1 and point P R1. So we know the rule V, which is equal to V1 plus V2. So V1, you have to apply the formula for this charge, you have to apply the formula for this one, and you have to apply the formula for this, and finally when you just add everything, finally you will get this relation. It's the concept of superposition principle. Clear? And finally we just come for the important topic, equipotential surface. My dear, you will get some theory question from this chapter, from this point, from this part. So what is equipotential surface? Could you please read the first line? What is given in this line? Any surfaces with same electrical potential. For example, you can see this picture. Here I have a charge, and this is my charge, and the blue color lines are my electrical field lines, and you can see the orange color dotted line, and all these dotted lines are my equipotential surface. How many equipotential surface I have in this picture? I have one equipotential surface, another surface is here, another surface is here, another surface is here. Am I right? So in this picture, how many equipotential surfaces are there? How many
4.
equipotential surfaces are there? 4. Now, my dear, you can see, is this equipotential surface crosses each other?
No.
No.
So your equipotential surface, never any two equipotential surface join together. All the times, each and every equipotential surface will be separated with some distance. Now that is not a matter, but if you just take the first circle, so if you want to find the potential here, if you want to find the potential here, here, each and every point in the first layer will be the same value. When you come for the second circle, the potential will be the same, but the values will be different, because we already studied. Closer to the charge, potential will be greater. Whenever you are moving away from the charge, potential will be decreased. Am I right? Am I right or not? For example, my first layer has 50, for example, 50 volt. My second layer has 40. My third layer has 30 volt. My fourth layer has 20 volt. Now you can see this 50 is for the entire surface. Clear? And this 40 is for the entire second surface. And this 30 is for the entire third. Any point on the equipotential surface will have the same value. Clear? Clear, my dear?
Yes, yeah.
So if you want to move any charges on the same surface, the net work done will be 0. Why? What is the reason? If you want to move a charge on the same surface, what should be the work done, my dear?
What, doctor, your question?
My question, I am going to move one charge. For example, I am going to say this. I have 4 equipotential surface in this picture. Am I right? Am I right or not? This is my equipotential surface 1, 2, 3, 4. Am I right? Am I right or not?
Yes.
So I'm going to say
Yes.
the equipotential surface has the value, for example here, sorry my dear, I have the equipotential surface on this layer is 50 volt, and here 40 volt, here 30, here 20. Now I want to move one charge on this surface from this point to this point. So what should be the work done? So this point also 50 volt, this point is also 50 volt. So what should be your work done?
Zero. Zero.
Zero. So if you want to move any charges on the same equipotential surface, what should be the net work done? Zero.
Zero.
Clear? Clear? Suppose
Yes.
you want to move the charge from one layer to another layer. That means one equipotential surface to another equipotential surface. So by the time 50 minus 40, you will get some value. So if you want to move the charges from one layer to another layer, you will get some net work done. But if you want to move the charges on the same layer, your work done will be zero. For example, you can see this picture. You can see this picture. I just gave some relation. You can see here. I have four paths. Path 1, path 2, path 3, path 4. You can see my path 1 is here. So now I just move from one point to another point on the same potential. So what should be the work done?
Zero.
Zero. Because all the area, especially in this layer, each and every point on the first layer have the same value. So if you want to move from one point to another point, what should be your net work done? It's zero. So potential will be automatically zero. For example, I say 50 volt. 50 volt minus 50 volt, which gives you the zero. Now let's come for the second. What is your second path? You can see I am in the third layer. I'm just moving from this point. I'm just moving from this point. I go to fourth layer. Again, I come back to the third layer. So what should be your work done?
Zero. Still.
Why?
Because it's still the same
Still the same, because each and every point has the same value on the layer, third layer. All right. Okay. Let's come for the third layer, third path. You can see third path. I'm just moving from first layer to the second layer. So what should be the work done, my dear? In this case, your work done will not be same. It will be have some value. It will not be zero. Am I right? So I just move the charges from this potential. So Q is my charge. I just move from Q2, V2 to V1. So I will get some value here. Am I right?
Yes.
Am I right?
Yes.
And likewise, fourth path. You can see my fourth path. I just move from V1, then I come back to V3, then I just move to V2. So two layers are different. In such a case, I will get some work done. Clear? Clear, my dear? Okay, here I just gave some information about the equipotential surface. So what is given in the first point? Any points on the same surface will have the same value. Clear? For example, if you take one surface, each and every point on the surface will have the same potential. That is the information for the first line. What is given in the second line? Your electrical field lines is always perpendicular to the equipotential surface. You can see here, my dear. You can see here, all dotted lines is my electrical equipotential surface. All blue color lines are my electrical field lines. What is the angle here, my dear? What is the angle here? What is the angle here?
90, Doctor.
90. That means it's exactly perpendicular to each other. Your electrical field lines are exactly perpendicular to the equipotential surface, and that informations are given here. Clear? Suppose if you want to move the charge from one point to another point on the same surface, what should be the value? What should be the value? Zero. The net work done will be zero. And I told you, your equipotential surface never join each other. So no two equipotential surface intersect each other. What is the meaning for intersect? Joining. You can see the picture. I have four layer. Is this four layer joined together? No. All four are separated with each other. Am I right? It's separated with some distance. So your equipotential surface never join each other. It will be always separated with other surface. Clear? And then the last one, yes. If you have a uniform electrical field, your equipotential surface is normal to the x-axis. You can see here, I have the blue color line. This is my uniform electrical field, and all this orange color vertical line is my equipotential surface. And you can see it will be exactly normal to the x-axis. Suppose if you say this is my x-axis, this is my y-axis, you can see my electrical field is always parallel to the x-axis. Clear? Clear, my dear?
Yes, clear,
Doctor.
Okay, let's come for our last topic. This is our last topic of this chapter. It's very easy. I explain everything in the easiest way. Now you can see, my dear, in this picture, I take only two equipotential surface. So this is my first surface. This is my second surface. So the potential in this layer is V, and the potential in this layer is V plus delta V or dV. Clear? So I told you already, each and every layer has its own different voltage, own potential. So according to this picture, my second layer has the potential V, my first layer has the potential V plus dV. So what I am going to do, I have these two potential surface and I am going to choose 2 points from each layer. That means point A from first layer, point B from second layer. Now what I am going to do, I am going to take one charge, small charge dq. I am going to take this dq from A to B. So now you can see the picture, all these black color arrow marks, this is our electrical field lines. Your electrical field lines will be going in the upward direction, but you are moving the charge to the downward direction. Now, my dear, listen carefully. What should be the work done? The net work done, which is nothing but the charge. What charge I am going to take? I am going to take dq, and what is the potential difference? This potential minus this potential. So what you will get? V plus dV minus V. So what will happen? This plus V minus V get cancelled, and finally you got this work done. Am I right? Am I right?
Yes.
Am I right?
Yes.
And second, we have another formula for the work done, because we know work done which is equal to force multiplied by distance. And you can see this is my small distance dr, and I am going to move the charge from point A to point B. My dear, we know the formula F dot dr, which is nothing but F dr cosine theta. What is the angle? My electrical field lines are moving from bottom to top, but I am moving the charge from top to bottom. So both are moving opposite to each other. So what should be the angle? What should be the angle?
180.
180. So cosine of 180 becomes negative. So I just take minus E minus F dr. That's it. Now we know the formula for the force. What is the formula for the force? We know formula for the force is nothing but electrical field multiplied by the charge. Am I right? Am I right or not? Force which is
Yes.
equal to electrical field multiplied by charge. But what type of charge we have? We have only dq, small charge. So in this place of F, I am going to take this value. I have to substitute here. So I will get F which is equal to E dq, and then another dr is here. So I just write it here. Now I am going to compare equation 1 and equation 2. So when you just compare, what will happen? My left hand side of the equations are exactly same. So I can equate with the right hand side. So dq dv, which is equal to minus E dq dr, this dq and this dq get cancelled, and finally I have to rearrange this equation in terms of electrical field. Therefore E which is equal to minus dv over dr. My dear, listen carefully. Here R represents the position vector, and you can see what is the beauty of this relation. Your electrical field is the vector quantity, and but your potential is the scalar, because electric potential is not a vector quantity. It has only the magnitude value, but your electrical field has both magnitude as well as the direction. Clear? One more theory question. What is the relation connecting electrical field and potential? Electrical field is a scalar quantity or vector quantity. So potential is scalar quantity or vector quantity. We may ask this question in the multiple choice question, especially for the theoretical part. So you must know each and every word clearly. Clear? Understand?
Yes, doctor.
Okay, now I have to conclude this, my dear. I just wrote this relation. My dear, I think you will study these things in calculus 2 or calculus 3, I think so. And this indicates the gradient form. My dear, if you just see, just before I write the relation, E which is equal to minus dV over dr. R stands for x-axis, y-axis and z-axis. But when you just partially derivate, when you just find the partial derivative with respect to x-axis, then you have to write dou over dou x. Am I right? Am I right or not? Inshallah, you will study these things in the calculus, and this is representing you are finding the differentiation of partially with x-axis, partially with y-axis, partially with z-axis, and all these partial derivative is nothing but the gradient symbol. Clear? Clear, my dear? Clear?
Clear, doctor.
This means, Doctor, all axis.
All axis, yes, absolutely correct. So E which is equal to minus gradient of potential. So this gradient indicates partial derivative with respect to x-axis, partial derivative with y-axis, partial derivative with z-axis. But generally we will ask the question for only one dimensional point of view. So in this place, so R, you have to replace this R with x. So this is for only one dimensional. If the question is related with the x-axis, you have to write x. If the question is related with the y-axis, you have to write minus dv over dy. If it is z-axis, minus dv over dz. But generally, all the times we will consider the x-axis concept. So please don't forget this formula. Clear? Clear, my dear?
Clear, Doctor.
So these are all the okay. Actually, this slide is just information about the conductor, because we already studied in chapter number 23. Conductor, all the charges will be sitting only on the surface. There will be no charge at the center. Am I right or not? Yesterday only we studied. You cannot be able to find any charges inside the conductor. If there is no charges inside the conductor, there will be no electrical field. If there is no electrical field, there will be no potential, especially for inside the conductor, not outside. Clear, my dear? Understand?
Yes, just on the surface. It will be
So this is just a theoretical concept. If you take a conductor, all the times the charges will be sitting on the surface. But inside the conductor, you cannot be able to find any charge. So if there will be no charge, no electrical field, no potential. So these are the collective formula what we studied today. But this formula, I just took it from the chapter 11. So sorry, chapter 21. So don't worry about this formula. We already know this formula. Am I right? You studied this formula in chapter number 21. Am I right or not?
Yes, Doctor.
But the most in this chapter, this one, and this one. Clear? Clear, my dear?
Clear, Doctor.
So these are all the three important formulas, inshallah, we are going to use in these 5 problems. So we are going to discuss these 5 problems in next week. My dear, listen carefully. I'm going to make the announcement in your blackboard about your quiz 2. What are the chapters? What are the chapters? Chapter 22, chapter 23,
23,
chapter
24,
24, in week number
11.
11. Very good. So we have
Doctor.
1 periods on Monday. So you are going to write this exam, write this quiz 2. So I can write here. So quiz 2 in week number 11, these 3 chapters. Clear?
Doctor, how many
Yes.
questions?
Like same like your quiz 1. I think I asked 8 questions. Am I right? Am I right or not?
Yes.
Yes,
So maybe this time 3 chapters, because your quiz 1 is 2 chapters. This is for 3 chapters. So I can make 10 questions. Instead of 8 questions, I make 10 questions.
Okay, thank you.
Clear? So once I prepare
Clear.
the question, I will tell you how many marks, how many questions. Okay?
Okay.
That's it, my
Thank
dear.
you.
Inshallah, we will just see in the next class, and by that class, I will finish this chapter 24. So we are ready for quiz 1, quiz 2. So you have to take preparation for your quiz 2. Try to take full marks in quiz 2. Clear? It will be very easy, and only few formulas we studied from these 3 chapters. Chapter 22 is the electrical field. Chapter 23 is the Gauss law. Chapter 24 is the potential. Clear?
Yes.
Clear, my dear?
Very clear, Doctor.
Okay, my dear. I think today the session is over. Inshallah, if you have any doubts, you can just contact me through the WhatsApp group, or you can just come in the discussion class next week. Clear?
Okay.
Yes,
Thank you.
clear.
Yes, Doctor.
That's it. That's it, my dear. Inshallah, we will meet in the next week.